Being at CppCon has been amazing because you can directly speak with the experts. I've had conversations with Bjarne Strusepp, with Sean Parent, and they're all very friendly and accessible and willing to give their opinions or advice on C++.
Okay, hello everyone. I think this is my cue to start. Good evening, good afternoon. I'm still working in Eastern time, but I know it's like late afternoon. Hopefully you are on your second set of coffees, and I hope we can make this as fun for you guys as it was for my team and I to work on. So I'm Kusha Maharshi. I'm a senior software engineer at Bloomberg, and today I'm here to talk about how we use distributed trace for generating end-to-end latency metrics. Now, before I really get into the nitty-gritty of it all, I want to kick us off with a little story. So I work on the telemetry infrastructure team at my company, which means that our goal is to provide telemetry solutions to the rest of the firm. Now, telemetry, if you're not familiar, it's really just a way to track the health of the different systems at our firm. And so we are tasked with collecting and providing that data. Like, how fast is your service running? How many requests failed? How many cache hits did you have? All of that good stuff. Now, our clients are essentially other engineering teams at the firm, right? So these clients build systems and products like trading systems, messaging systems, news platforms, and all of these different products have to be high throughput, low latency. So our clients, our engineers, are essentially dealing with large volumes of high stakes data that must be handled very, very fast. And especially in the financial sphere, even just a few milliseconds of delay or latency can mean millions of dollars lost. So in order to prevent latency from creeping in, the engineering teams at our firm really need to monitor their complex distributed systems. And in the modern technical architecture, right, like nothing happens in isolation. If you click your online checkout button on a shopping website, that's triggering the interaction of numerous services with each other. And so naturally, in order to monitor some user action or user experience, we're going to have to monitor complex architectures. And so, as a result, we saw this recurring request at our firm, which was the need for latency metrics for end-to-end workflows. Now, what do I mean when I say that? I simply mean that our engineers were saying, hey, if I've got a service A that talks to service B, that talks to service C, then please give me the timings of requests going between A and C. So give me the timings of requests in this end-to-end workflow. And previously, what we had was either engineers would use service-wide metrics, so you have a view of what a particular application, a particular database is doing, but not that cross-service view. Or we would have teams that would build their sort of own custom end-to-end tracking mechanisms, like passing around a session ID, passing around a request ID. And that is where as the telemetry providers at the firm, we wanted to utilize distributed tracing to be a unified, centralized solution for this all, especially as it was like gaining adoption at the time. Now, I'll pause right there. If you're not familiar with distributed tracing, let's take a look at a quick example for what it is. In simple words, it's a way to track and visualize the flow of requests through a complex distributed system, right? So if you just look at the screen right here, all that's happening is, if you can follow my cursor along, some user made an API request, then that request went to be parsed by a service, and then eventually that service made some calls to a database to get some data and handle that request. Very generic workflow, right? And now, this flow of the request through this multi-step, multi-component system is represented by what's called a trace. And every single little kind of block that you see here is a span. You can think of a span as a building block of a trace, every like little node or hop or step in the way of the request. Now, some salient features about distributed trace Every trace is identified by a unique trace ID, and every span in a trace is identified by a unique span ID. Also, you will notice that I've got these yellow arrows pointing here. These arrows are essentially signifying parent-child relationships between different spans. So what this means is that this parse request operation called this database read operation, which really means that we are pointing, the callee is pointing to the caller. And each span will hold references to its callers. And then finally, one more important thing, which is why we're all here today, spans hold important timing information. So this timeline that you see up here on this dashboard, image, is essentially showing us that, hey, I can now tell when this API request operation started and when it ended, when parse request started, when it ended, and so on and so forth. And then spans hold like some important like metadata about like what machine it came from and so on and so forth. Now, coming back to our story, so that was what distributed tracing is, and we were like, okay, this is a solution that can be a unified way to get end-to-end latency metrics. But very, very quickly, we learned that our firm's trace data is quite complex. It was very, we saw a lot of long traces. We saw a lot of traces with complicated parent-child relationships that are not the easiest to scale, and we'll talk about that in a bit. And obviously, it was happening at a high volume with over 50 billion spans streaming into our system every day. And that's why we decided to build a C++ solution to handle this problem, to get end-to-end latency metrics at scale from trace. Because of the complexity and nature of our trace data, commercial products or open source solutions didn't quite fit our needs, and so we built it in-house. Now, before I kind of dig into what we did and how we got here, it is going to be a lot of information in a little time, but I will be following things up with like examples to make things clearer. But of course, at the end, we'll have time for Q&A, and we can always chat in the hallways for things that did not make sense. All right, so I want to start us off by talking about a real-world example of an end-to-end workflow, and we'll kind of use this throughout the presentation as an ongoing example. And this is essentially a pipeline representing an equity order execution system. Now, if you're not super familiar with financy things, don't worry, I'm right there with you. Like, prior to, I'm an infrastructure engineer, so I only know this because of interviewing our users, and prior to that, I would also just be like, I know we're trading, but I don't know what's getting traded. So bear with me here. But this is a very contrived, generalized representation of an order execution management system. You can think of it as you've got different traders as your clients, right? And they are placing equity orders, maybe something like buying Apple, Microsoft stocks. And then these orders are going through what's called brokers. And these brokers sort of like handle those orders, and then they generate what's called fill messages. Each fill message contains important information about the status of execution for that order, as to how much of it was successfully completed. Then that goes through an order management system, which does fun order management things. And then that goes to a Kafka queue. If you're not familiar with Kafka, and we'll be using this a lot in this presentation, it's essentially a distributed data store, which enables the ingestion and processing of streaming data in real time. Simply put, it's a message queue that allows for good scale and partitioning logic. And then we've got a publisher service that pulls things off this Kafka queue in batches, processes it, and publishes it out to different subscribers, which eventually ends up in traders being able to view the status of their orders. Now, this is sort of this end-to-end pipeline of how traders can view the status of their orders, and you can imagine if there is a delay in viewing these order statuses, that's not cute. Like, no one wants to see that, and that delay can lead to lost monetary or investment opportunities. And that's exactly why we need to monitor end-to-end latency of this pipeline. So to kind of just summarize why we need to do end-to-end latency monitoring and why we're here today, in simple words, it allows us to quantify and measure user experience in complex architectures, which is all architectures today. And then if we have these important latency metrics, then anytime something's slow, there's a spike, then engineers can be alerted quickly in real time so we can act before there's any noticeable client impact. And then it also helps us establish SLOs, which is service level objectives. These are essentially measurable targets for reliability and performance. So an engineering team can have an SLO like, we want to make sure that 99.9% of our requests finish within 1 second. And these are also very valuable for engineers, managers, and executives alike to get an understanding of the state of the overall system. Now, finally, this is also important for design and development, which is that if you're testing out different architectures and pipelines, you can use these like end-to-end metrics for A/B testing as well. Okay, so with that, okay, I'm gonna quickly pause because my clock is not working, but I'll also set one on my laptop right here. But yeah, just letting you know. All right, let me go here. Okay. So let me come back to now the example that I shared before. So going back to this equity order execution pipeline, right? I want to zoom in on this little part of the pipeline that is circled in red right here. And this is what we'll use as our example. Let's think about this end-to-end workflow that is consuming something from the Kafka queue and then publishing it out for these eventual users to view. And now I want to look at what the example, like what the corresponding distributed trace for this looks like, right? So you will see on your screen right here, we've got 3 main points in this workflow that we care about. I consume from the queue, and I consume these messages in batches. That's just a feature of it. You're consuming in batches for efficiency. And then I process them all together, I publish them out to the clients. Those are the 3 main steps. And you will see that visualized right here in this top trace with the consume span, the process span, and these 2 little publish spans. You will note that I've got this yellow arrow pointing to 2 different trace IDs, which refer to this trace and this other trace. Now, what's that? So remember I told you that spans hold references to their parent spans, to their caller services, right? In this case, obviously, I know that this process was called after consume. But why do I have these references to these other 2 consumes in these other 2 traces? Well, this is a common pattern that emerges in queuing and batching steps in complex systems, which is essentially when you've got many different requests that started, and at some point they all come together and then are merged in a way and then handled all together to go forward in the rest of the workflow. And this is kind of like an interesting pattern that we will work with and will end up being a cause for a lot of our problems. Okay, so with that example, I want to take it one step forward, and I want to establish how a trace is actually essentially just a directed acyclic graph, right? So if you look at this image, you will see that a span is basically a node. And each node in this shorthand notation has a trace ID, a span ID, and the operation that it corresponds to. The same references that we talked about are maintained in this directionality of this DAG. And you will notice that this process span here has 2 children nodes in these publish nodes. This is a classic pattern of a fan out. And you will also see that this process span has 3 different parents, which is what is called a fan in. So recall the same pattern of many requests coming together at one point to then get handled. That's your fan in pattern represented in a DAG right there. And we know that these are coming from 2 different trace IDs as they were originally different requests. Okay, so I've been talking a lot about how we interpret trace, how we interpret requests, how we interpret workflows. So now I want to take a moment to talk about how our users interpret workflows and how they interact with us as the telemetry providers. So, think about the team that manages that equity order execution system, right? What they would do is they'd come to us with a rule. A rule essentially defines an end-to-end workflow. They'll come to us and then say, hey, get me the latency of requests going from consume to publish so that I can then view them nicely on a dashboard and see how my system's doing over time. And then they're able to define obviously give the rule a name, consume to publish, let's say. They're able to define a starting point and an ending point. That is consume and that's publish. And then finally, we're able to see, just taking a look at the example trace we've been working with, there's a start point and an end point. And we will call these points events. An event is essentially just a way to identify a set of spans. So all the spans that match the consume operation, all the spans that match the publish operation. So that's your start event and end event. So that's basically what a user needs to do in order to get their end-to-end latency metrics. So with that, now I want to actually go to thinking about how we would get this end-to-end latency from just one trace. So we're not talking about over 50 billion spans a day. Let's just look at these 4, right? And we know that our start event is this consume operation. Our end event is this publish operation. Really what we need to do, given that we have the timings on these spans, is basically relate this publish to consume and get the differences, right? And so in order to do so, what we simply do is we run a DFS through this DAG from bottom to top. It's bottom to top because spans store references to their parents. And then, similarly, we can do this for this other highlighted path. So there's like multiple different valid paths through the system, which are representing the latency of different requests going through the system, right? And all that we're trying to do is we're trying to find the difference between when my start event started and when my end event ended. And that's your answer. So for these 2 different paths, for example, we could have maybe like a 3 microsecond and a 3.5 microsecond. And then at the end, some metrics dealing aggregation magic later, which would be a whole other presentation of its own. What we get is these latency metrics that users, that engineers can then view on their dashboards. Okay, so that's how we can do it for just one trace. Now, what happens when we extrapolate this to 50 billion spans a day? How do we handle it at scale? So this right here is an architecture diagram of a hypothetical solution for handling this problem at scale. As the telemetry providers, our sort of like ingestion point of this data is often Kafka. So we ingest all these 50 billion spans a day into a Kafka topic. This Kafka topic is the one that I have shown right here. These spans are sort of like just spread across different partitions in random ways. If you're not familiar, a partition in Kafka is essentially just a way to group together logically related entities, and it really helps scale up your system as your volume grows. So now I've got my spans coming in, right? Like they're coming in and randomly spread across partitions. I've got this service called the partitioner, and as the name suggests, it's tasked with repartitioning these spans and putting them into a new Kafka topic. So what this is doing right here is, if you take a look, our 4 spans from trace 1, our favorite example, were in different partitions before, and now they've ended up in the same partition. So we have now guaranteed that all spans from the same trace ID will end up together. Why are we doing that? So we can do that DFS that I just showed you. And then we've got this service called Dagger. It's called Dagger because it works with DAGs. I'm so funny, yay. And then it will run the DFS and it will generate your metrics and you can then view on your dashboard. So pretty easy, makes a lot of sense, I hope. But if it were that easy, I wouldn't be here talking about this today. So what's the catch? The catch is, drum roll please, fan-ins, right? So we were looking at this like isolated trace and what happens when we're dealing with just one trace and everything is nice and easy. But what do we do when you've got this scenario that we just looked at, right? When you've got the case where you have these valid paths, you have these queuing, batching type patterns in your complex architecture that manifest as these fan-ins in the data that we see as the telemetry providers, right? Because in this case, all of these 4 DFS paths are completely valid and their latency should be monitored. So to kind of summarize the problem that we're dealing with right now, we're just trying to make sure that we have a way to scalably get end-to-end latency metrics when you've got fan-ins. How do we partition? How do we kind of scale up our data in a way that we have access to all of these spans in one place? And you can think of our kind of end goal as making sure that all spans in a weakly connected graph, in a weakly connected DAG, are handled together. That's for any graph theory nerds in here. But for our purposes, we'll just call it a trace bundle. So a set of traces connected to each other through fan-ins all are part of a trace bundle. And our goal is to make sure that all spans from a trace bundle end up together so we can run our DFS on it. All right, so with that, I'm going to talk about actually the two approaches that we took to handle this problem, to handle fan-ins. But before I get into the real nitty-gritty of those approaches, I want to highlight a common underlying factor for both of those, which is why we're here, C++. And for us, it was really important to design for speed and scalability from the beginning, which is why C++ was a natural choice. Because of having better memory control through, move semantics, references, and pointer management. Also because of enabling concurrency at scale through multi-threading library support, which is further supported by our internal wrappers around it. So that just speaks to a well-developed ecosystem. And then, of course, being able to rely on performance standard data structures. And then finally, the mature ecosystem of C++ is rich with tooling that we can use for like debugging and testing and whatnot. So we go from there. We have these like two different approaches that we really just took a journey through to implement, and like we'll find out what happened in a second. Now, I want to give you a quick agenda overview for the rest of this presentation. I just spent a lot of time setting up terminology, giving a lot of background, and we will now really dig into what these implementations were. I will start off by talking about the designs for these approaches and what were the different microservices that we implemented to handle this problem. And then I'll go into some C++ level data structures we used, and then I will pinpoint some implementation level bottlenecks that we encountered along the way and how we use profiling to improve their performance. And then finally, I'm going to summarize the pros and cons of these approaches and hopefully leave you all with some key takeaways from our journey. Okay, so with that, let me get into approach number one, and that is aggregating trace bundles by rule. What does that mean? So we just talked about what a trace bundle is, right? Which is all of your traces connected with each other through fan-ins. So I'm going to start off at this Kafka topic right here, which is partitioned by trace ID. So remember, recall in that initial diagram we saw, we had this partitioner service, which led us to this topic partitioned by trace ID, guaranteeing all spans from the same trace ID end up all together. Now, I've got this service named bundler, which essentially will send all spans in a trace bundle, matching a rule start event to the same partition. Whoa, I know that's a mouthful, so let me break that down. So this bundler service has two goals. Goal number one, if you look right here, you will see that all the spans from T1, T2, and T3 have ended up together in one partition. So goal number one is to make sure that spans from the same trace bundle land together. And then goal number two is to filter those out by a potential rule match, which is to say, I don't want to bother with sending any traces forward into this Kafka topic if it doesn't even match a start event of a rule, if it doesn't even have a consume span. So that is another task of this bundler service. And then finally, in this case, we are partitioning by rule, which means that all of the trace bundles that match a given rule potentially will end up in the same partition. And then finally, we're back to having our favorite dagger service, which will run the DFS and generate the metrics. Okay, that did not make any sense. I completely understand. And so let's work through a little example. So let's really zoom into what this bundler service is doing, which is where most of the complexity here lies. And if you take a look, I've got a little new Kafka topic right here, which we didn't know about before. So what is this? Essentially, we've got a small Kafka topic that is working in between all the different instances of bundler. This Kafka topic essentially is enabling gossip or any communication between these different instances. The main types of messages that flow through this Kafka topic are fan-ins, messages about fan-ins, and about any trace rule matches. So what does that mean? Let's assume that this bundler 1, gets our spans from trace T1. They're streaming in from the Kafka, flowing into bundler 1. Bundler 1 sees that there's this consume span, and it will be like, oh, wow, that's a match. I know that this is the start event of our favorite rule, consume to publish. And then it will see this process span. And it will notice, oh, process has 2 parents in different trace IDs, so I know that that's a fan-in. And because it's a fan-in, and I might not have access to all of the trace bundle, let me make sure that the other bundler knows about this too. So what it will do is, it will send some messages, some communication to bundler 2. And it will say, oh, by the way, T1 and T2 are fanned into each other. T1 and T3 are fanned into each other. And also, I know that T1 potentially matches consume to publish, which is our rule. And by doing this sort of like inter-instance communication, our goal is for all of the bundlers to have a complete view of the different trace bundles that are getting streamed into our system. And more specifically, what we want is for bundlers to be able to maintain these in-memory maps that essentially completely define the state of the system and what traces are in what bundles. So let's take a look at what these in-memory maps look like. So each bundler will have its own copy of these maps. And there's 2 main maps that I want to focus on here. So this one is essentially a map that is going from a trace ID to all the trace IDs that are part of a bundle. So in our example, we know T1, T2, T3 belong to a trace bundle. And all the rules that potentially match a bundle. In our example, that's consume to publish. This select trace ID is simply just a trace ID we will use to represent a trace bundle. You can pick it to just be the numerically lowest trace ID of all. Now, we have this other map that is essentially a reverse lookup map, where we go from every single trace ID that's in a bundle to what's the representative selected trace ID that we used. And we need these 2 maps so that anytime I have a trace coming in, I can easily look up what are the other traces in that bundle and what are the rules that match that bundle. And if I have a T2, a span from T2 that comes in, I can be like, oh, I know that that maps to T1, and I know that the other traces in that bundle are T1, T2, T3, and I know that that matches the rule consume to publish. And then, if you recall, we can then flush those spans out to the right partition, which is partitioned by rule in our output Kafka topic. And from here, I want to go one step further and then see what these data structures look like at a C++ level. Pretty straightforward. We've got a bunch of unordered maps and unordered sets. This is really your trace to bundle key, which is your reverse lookup map, going from a trace ID data type to a trace ID data type. We've got a struct where we can store all the rules and trace bundle traces. And then we've got our big map where we're capturing what trace bundle key maps to what set of bundles and rules right here. And I mean, the reason I'm showing you these data structures is because now is when I want to take a small detour to talk about, as we are implementing this architecture, one of the implementation level bottlenecks that we ran into. So the state of the system wasn't always this way, actually. We didn't always use these 3 data structures. We actually had something that looked a little different before. And what happened when it looked different was that we were noticing that handling these messages coming in from the gossip Kafka was taking very long. So doing these updates to our maps was taking very long. And that's because previously we had this extra data structure called trace to rule flush indices. If that sounds really complicated, it is because it does indicate that it was overly complicated and we probably didn't need it. But Basically, what this data structure is doing is we were actually storing every single rule that matched every single trace and how many spans from that rule we'd already flushed to Kafka. It's okay if you don't understand what I'm saying right now, but we were storing a lot of information that we probably didn't need to, because we realized that really what we needed was the rules that match a trace bundle, not the rules that match a trace. Now, as a result of that, what we did, because it was so slow, we ended up profiling using perf and then viewing it as a flame graph, that bit of code that's handling these gossip messages coming in. And then we noticed that all the time, most of the time, in handling these gossip messages was just getting spent on doing lookups and writes in this trace to rule flush indices unordered map. And that's when we realized that this actually is a premature optimization, and we removed it. Why did we have it there in the first place? The small trade-off benefit that it had was it allowed us to cut down on some data duplication, which we can talk about later if someone's interested, but it wasn't necessary in the grand scheme of things because it was slowing down processing. And so in that case, being able to profile a small bit of code and being able to really see what's going wrong helped us sort of move forward. And with that little detour, I want to now just review this solution really quickly one time. We have our spans coming in to our partition by trace ID Kafka topic. A service bundler is going to repartition them by trace bundles and put them for all of those for the same rule in the same partition. And then our favorite service Dagger is going to run the DFS and generate some metrics. And the key, the crux of this approach is that we are trying to put all the spans from the same trace bundle in the same place for an instance of Dagger to be able to handle. And this approach works pretty well when rules match a small portion of your traces. And one of the constraints of this approach is that it can lead to some load imbalance, which means if you've got some rules that match a really large volume of traces compared to others, then obviously you can incur some load imbalance in terms of Dagger's memory. So for example, if you've got rules that run on some type of middleware spans that you expect to see in most of your traces, that is going to lead to load imbalance. Additionally, remember how we're putting all the traces in the same bundle together? That will further exacerbate that issue because we're adding to the memory because of this fan-in bloat that I like to call it. And so, because of this constraint and this approach, we wanted to see how we can sort of future-proof it for scalability as we onboard new rules and maybe onboard heavier rules. And that's when we sort of thought about approach number 2, which is what I'll get into now. Okay, so approach number 2 is essentially one where we hand off a partial DFS. So what does that mean? Once again, we're starting off at our favorite little Kafka topic that is partitioned by trace ID. This time, Dagger's consuming straight up from this Kafka topic, right? So all spans in the same trace are ending up in the same Dagger instance. And now, this Dagger is going to start running the DFS, as we saw in our examples. And then it might run into a scenario where it doesn't have, let's say, a T2 or a T3. And when that happens, it will simply communicate to Dagger 2, oh, I couldn't finish the DFS because I don't have the trace, but could you do that for me? And then Dagger 2 would finish up the DFS, generate the latency metrics, which get aggregated and then put out to your latency dashboards, metrics dashboards to view. Just for the sake of time, I'll skip the detail on aggregation, but that's really not the point here anyway. Okay, so to make that make a little bit more sense, let's take a look at an example. Once again, we've got ourselves a small Kafka topic that we're using just to communicate between the two Dagger instances. What this Kafka topic is doing is, well, first, it's partitioned by the fan-in parent trace ID. What does that mean? Well, if I know what trace I'm looking to finish my DFS on, then I know what partition to send it into for a specific Dagger to consume. And let's take a look at what the messages going through this topic look like. So once again, we've got some spans streaming into Dagger 1. You will note that I'm starting off with a published span for ease of understanding on the diagram. But what's going to happen in Dagger 1 is it will start doing a DFS on publish, which is, remember, the end event. Then it will start working its way upwards. It will hit the process span, and it will see, oh, I've got myself 2 parents in trace 2 and trace 3 that I don't have. I don't have access to trace 2 and trace 3. So what I'm going to do is, I will send that message across to Dagger 2. I will tell Dagger 2 that, by the way, I started a DFS, but I couldn't find trace 2 and span 21. Do you have it? I mean, in this case, it knows that it has it. And it will say, I know that the ending time of my DFS was something something because it was able to extract that from publish. And then it will say what rule it is trying to match for, which is consume to publish. Similarly, it will do that for trace 3 right here. And then Dagger 2 is able to sort of complete that handed off partial DFS by matching the consume spans in trace 2 and trace 3 that it has access to. And so to sort of summarize that, what I'm trying to say is that anytime you run into a fan-in situation, we are just handing that off to the relevant Dagger to handle. Okay, so now I want to take a second to zoom into the C++ level data structures in Dagger. Obviously, these are not all the data structures, super small view of it, but a super key kind of struct that we use is just the one that holds all the spans that are coming in and a vector of the rules that potentially match those. And then another super key data structure is all the traces that we have to process to do the DFS. And that is just holding a trace ID and a pointer to all the trace data in it, which is all the spans and the rules. And then finally, which is key to this particular solution, this particular approach, is that we hold a data structure, which is a buffer of, hey, what are all these like partial DFSs that we are yet to process? Okay, so that is, again, I'm sharing this with you so then I can talk about at the implementation level, what were some of the issues that we ran into as we were trying to, run DFSs on these data structures. So what we were starting to see is that processing some of these traces took very long. We would see this case when just one trace would take like several seconds, which does not sound right and should not be happening. And so here I want to introduce a special user configuration. So, again, let's talk about that equity order execution team. It comes to us saying that give us a latency between consume and publish for our rule consume to publish. They can also tell us some other things like, oh, actually, I want to use an advanced configuration and I want you guys to skip the DFS. Don't do the DFS in your latency end-to-end metrics calculation. We don't need that. What does that mean? So if you really think about it, remember, if your start event and end event are in the same trace, we actually don't need to do this DFS situation, right? We can simply just be like, time of publish minus time of consume, end of the story. Time of publish minus time of consume, end of the story. The only time we really need it is if we've got many start and many end events in the same trace. So if we've got something that looks like this, right? So this is the same trace ID, and some stuff is going on in here after this root node or this root span. And now I've got 2 consume operations, and I've got 4 publish spans. I can't just, get the latency of publish minus this consume because that doesn't make any sense. That's a false latency. That does not represent a real path that a request took in the system. So really, the whole reason we've been doing all this DFS in our daggers is because we see a lot of those cases in our trace data. So we have to do the DFS in order to get the true relationships. But some of our users, they know that their traces don't look like that. And this is a lesson in how you kind of talk to your users and figure out their needs, where it's like, well, we can simplify some of these calculations if you don't care about these more complicated cases. So some of our users can tell us that just skip the DFS, just do simple math, and that's all we need. So interestingly, in that simple math case, we were seeing the longest time spent. So what's going on there? So once again, we profile that bit of code. We profile what's happening in, well, I say DFS execution, I mean overall DFS execution, but really we're skipping the actual DFS. And we noticed that the culprit was repetitive calls to the event matching function. What does that mean? So remember how this whole concept of events is helping us match relevant spans. If I have a trace that looks something like this, where I've got 500 published spans, then what we were doing was we were constantly running your matcher function. Does this span match publish? Does this span match publish? Blah, 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 500 times. Obviously, that's going to add a lot of latency. And we were able to catch that by, again, using perf and viewing the flame graph and profiling that bit of code and seeing, that handling the single trace spends most of its time in just doing the matching and not even like doing its DFS or any other type of latency metrics or anything. And then we saw that, we don't actually need to do this several different times. I should clarify. What we were doing was we were running it 500 times also for this consume event, just because we had 500 publish events. And the fix was pretty simple. We just added a cache so that we wouldn't, rematch the same span we already know matches the start event. And once again, by using profiling, we were able to see what was really going wrong and then fix that. Okay, after that detour, just want to summarize approach number 2, which is what I like to call the lazy approach, as opposed to approach number 1, which is a greedy approach. We don't try to preemptively make sure that all the spans from the same trace bundle end up together. Instead, if and when, while doing a DFS, we run into a problem, then we communicate with other Dagger instances. So the good thing about this approach is that it avoids that load imbalance issue, because we're not preemptively building all these trace bundles. However, one constraint of this approach is that it doesn't work very well with deep chain fan-ins. So if you have a case where you've got a path of fan-in after fan-in after fan-in, then that would lead to a lot of these gossip hops in our system, thus incurring delays. But all of that is to say, in conclusion, that even though it's all complicated, end-to-end latency metrics can be generated at scale. And the key here is to pick the approach that's best for you, or a hybrid of approaches that's best for you, with some operational knowledge about your users. And one thing that was important to us was to design for speed from the start. And that's, we learned along the way to avoid premature optimizations and to constantly leverage tooling to iteratively improve code performance. And of course, finally, end-to-end latency monitoring is crucial because it really helps us directly quantify and measure user impact. And trace, distributed trace, is able to provide a unified solution to that. And finally, if you got nothing from this presentation, at least I hope you thought distributed streaming DAGs are fun. And with that, that is the end of the talk. And time for Q&A. I was told to let you all know to use the mic, which you already know to do.
So quick question, do you have a problem with clock sync, like wall clock sync between hosts?
So we don't, but I know a lot of people do, in the sense that full story. So remember how I told you how some of our teams have their own custom solutions? Mm-hmm. So even on the spectrum of being latency sensitive, some teams are super, super latency sensitive, and others need it within some range of correctness. Mm-hmm. And for that scenario, the super, super latency sensitive teams do use their custom solutions, which I know a lot of, especially trading firms and stuff, deal with the clock skew issue. Yep. We haven't handled that problem within this, but it is something that some teams would not like.
Fair enough.
Yeah, I know that. Actually, I read a research paper on someone who specifically did that for distributed trace. Mm-hmm. So if you were to look up distributed trace clock skew paper, you might find it.
Thank you.
Yeah.
Hi, great talk. My question was, what is what was your process for creating new rules, and what would need to be done in order for them to take effect?
Yeah, so a process that is a work in progress in the sense of it could be nicer, but what our users do is we kind of just have a GitHub repository that is user-facing, and users are able to use JSON like schemas and configuration to just be like, my start event matches this service, this operation. So right now it is like a JSON-based schema configuration system that users can give to us, and then once we get that, we essentially just have a way to send that to our backend, to like this system, to be able to grab all the new rules, and then they can take effect once they're received. We also use Kafka to like enable some of that transport.
Oh, so that can just like happen intraday without needing to bounce anything.
Yeah.
Oh, that's cool.
It is constantly
Okay.
streaming in the updates to user rules.
Awesome. Okay. Thank you.
Thank you. I know from Kafka and the multiple partitions, there are several problems around reordering and like the fact that things don't necessarily arrive in useful time orders. And the first thing I thought when I saw your slides that came up was like, how do you handle that? And more importantly, with things like the gossip protocol, how do you handle the fact that events could arrive at two independent brokers and cross each other? And therefore, that sounds like a painful thing to do.
It is very painful, and I could do a whole other hour
I figured.
on just that part, but the TLDR I'll give you is, so with trace, the big problem is you never know when it ends, right? So we essentially employ some type of heuristics based on what we've noticed about most traces in our system to be like, we wait, like we kind of buffer the spans coming in for a while, not ordered by anything. We wait for some amount of time to pass before being like, all right, heuristically, this is now good enough to process. And at that point, we don't worry about the order because at that point, we can kind of work with just what's matching our latencies, and then we're publishing these metrics based on the spans timestamps. So that's where we get that deterministic, like, okay, you're actually representing the time for the actual operation you came from.
Got it.
So to answer that, the main way in which we kind of handle the reordering issue is by buffering things for a while.
Right, and a heuristic for how long you think, well,
Yes.
nothing should take more than 5 seconds, so let's keep 5 seconds worth
Oh,
of
I
that.
wish it was just so simple. But yes,
Yeah.
a lot of heuristics, yes.
Thank you very much. Thank
Yes.
you.
Right. Thank you for the talk. Just one quick question. I'm kind of curious on how do you handle disaster recovery? Because now you have these daggers who are communicating with each other. They're holding all these things in memory.
Yeah.
What if one dagger is to just suddenly die? How do you recover from that?
Yeah. Honest answer, currently, you will lose that data. Future plans, we would like to persist that. Like, we do in a lot of models, where you have your pods that are holding stuff in memory and you're persisting it maybe through a write-ahead log, either to the disk on the machine and or through persistent volumes to storage. And we have not done that yet. That's the simple answer for now.
Gotcha.
But we would love to have that in there.
Got it. Thank you.
Yeah.
Hi, thanks again. Following Matt's question, and I think also this person's question, what if ops get stuck? So say everything's functionally doing what it's supposed to do, but things are getting stuck, piling up somewhere, and then it seems like the latency can't be reported until the operation is finished. So you may have some piling up stuck ops, and this relates to, for example, forgetting about things if they take too long, expect from the cache. So I'm just wondering about that. I'm wondering also about the freshness of the resulting data. So those are two different questions. The first one is the bigger one.
So just to make sure I understand it right, what happens when maybe something is too long and doesn't match your heuristics? Or what happens if something's not complete in terms of the trace data?
Say there's maybe a new release has a functionality bug that causes some ops to just get dropped in the middle of that pipeline.
Got it. Yeah. So great question. It is actually one of the things we're working on right now, which is this idea, which kind of helps handle that, which is this idea of what we like to call completeness metrics, which is essentially that not only are we giving you the latencies, but we're also telling you when something did not complete as expected, which could be because the user system wasn't doing well, or that their spans got dropped because of some network issue. And then we can alert the user that these are the number of times that you sent us something, but it didn't complete, it didn't have the spans you expected, and you should know that. And we are only reporting latencies from the cases where it was complete, and then we're reporting the cases when it did not complete at all. And in order to do that, we need some help from the users in that they will tell us some conditions like, okay, I expect this to take 5 seconds start to end. And if it wasn't within that time with some like buffer, then feel free to assume that this was a bad trace or something got dropped or something went wrong. And then report that to us as a separate metric. So that's kind of where we're at with like how to best handle that case.
So you guys have your spans reported at the beginning and the end with separate messages, or just at the end?
So the span, that's a good point, and I probably should have clarified before. A span contains both the start and the end of an operation. So it's got your start time and your finish time, and that's getting sent to us at once.
Okay, so at the end.
At the end of that operation, yes, because there's no way to like, yeah, it's not like that a span is emitted when something starts and something ends.
Right.
Once that operation completes, actually in the API, the way it works is your span will sort of get destructed along with the operation and get sent.
Yeah. So you have the problem that like you got this long chain of spans, but you could get some in the middle before the first one comes.
In terms of when we receive it?
Yes.
Absolutely. And that, again, this question you asked before, that's sort of how it gets sort of consumed within that bigger problem of timing, and we just buffer it.
Okay, thank you.
Yeah. Also, I'm not sure if this is the right clock. Oh, no, we have time.
All right. I noticed that you put up some C++ on the screen, and this is obviously a C++ conference and everything. Using the standard container. Are you really using the SDL for this kind of high-level thing, or because I saw a map of strings, which doesn't sound like a kind of thing that you would want to do in such a high-performance?
So great point. Actually, when we were sort of profiling things and looking for where to make the improvements, the string operations weren't taking up the most time. So we definitely considered, like, instead of using strings, to just use like integer-based IDs or string views, but we ended up not needing to do that. So one thing we kind of like to do is keep code simple unless necessary, premature optimization. So yeah, something we considered did end up needing to make it better.
Right.
Yeah.
Thank you.
Use BSL allocators?
No. Simple standard allocators. We will talk later.
Repeat the question for that, for the recording.
Oh yeah, so Brett asked if we use BSL allocators, which is our internal library. Can I say this? It's open source, great, I actually did not know that. Yeah, so we do not use any custom allocators. Yeah. Also something we have thought about.
So you have a rule to bundle multiple traces. How do you prevent the abuse when rule bundles everything and then your system is overloaded and your latency is 5 days?
So that is exactly what the problem with approach 1 was, where, you know, if you have a rule that is just having a lot of trace bundles matched up, and or if you have the case where you've got these like massive fan-ins into each other where like a trace bundle could be like several thousand traces big. So we do have a few things to that question. We do have some constraints in terms of like, you know, if your trace bundle is over a certain amount of size, we'll report it and drop it. And the user's most likely doing something wrong if it's like too big, and you know, they should probably fix their instrumentation. And for the part where all these bundles are coming in together for one rule, yes, that is a problem. That was a problem with approach 1, where you can see load imbalance as a result of that. And we wanted to prevent against that, which is why we kind of started looking at approach 2, where all the traces that match a given rule don't necessarily end up in the same instance, so they don't cause that like imbalanced memory overload. We don't have anything in place to be like, you're matching too many traces, because again, if you're like a middleware, right, like you're gonna match a lot of traces. Another thing we have done to kind of prevent against that is kind of like a side door in some cases where we only send spans that match the start and end event for the simple use cases. So if you're a user who has a lot of volume, then at least use that skip DFS option I was talking about. So far it's been, like I said, a mix of changing our approach and some user configurations to help reduce their load and some internal limits on how much they can send us.
Since we've still got time,
Yeah,
can
I'm
you,
surprised I finished on time. Great.
can you
So
share
much ahead of time.
the resulting data? So it takes some time to do this processing, aggregate the final latency data.
Yeah.
So some things happen, and then later on you have some data about the latencies.
Yeah.
What's
that delay?
Timeline? Yeah.
Currently, it is on a varying scale of 3 minutes to 6 minutes, which again, some work in progress things, trying to reduce that. So right now, most of that delay actually comes from the earlier question, which was, we need some heuristics to know when things are ending. So
Data freshness, yes? Is it data freshness?
Yes.
yes. So most of that delay is just coming from us being like, okay, well, I have to wait for a bit to be sure that your trace ended. Which is why what I was kind of alluding to before, having the users tell us when you expect it to end is something we're working on right now so that we can reduce that a bit.
All right.
Yeah.
And there's no one right behind me. You mentioned SLOs and something like, just as an example, on the slide, there said something like 99.9% less than 1 second.
Yeah.
So I've done some work with SLOs, and one of the things I've found is tricky is figuring out what period of time to make that commitment over. So do you find are people
Yeah.
committing to 99.9% of latencies per second or of latencies per month?
Yeah, so that would be a great question for an SLO expert, which I'm not, but from what I've learned from being on my team, and we do work with SLOs and handle that, is basically the way it works is we've got the idea. Are you familiar with burn rates and error budgets as well? Right. So they're really the ones that are kind of aggregated over different windows. Like in the last 1 hour, I used up as like X% of how many times I could go wrong, right? And in terms of that more granular metric where it's like 99% of requests should end up within that 1 second. So for our case, our metrics are aggregated by 30 seconds. So what we're seeing, the data we're consuming to make these SLO calculations is the value of like how many things succeeded in the last 30 seconds. So that is sort of like a kind of implicit default aggregation that comes in there. Did I misinterpret your question? Are you asking about the more like...
It must be a part of the Dagger, right? Because if you are doing like 3 nines SLO for latency, you need a lot of data. So probably it's just at least 24 hours rolling. But I assume it's part of Dagger, right? Part of user configuration.
Well,
Yes.
I think it's an interesting topic for whole teams to argue with each other about.
Yeah.
I have a follow-up question.
Defining a good SLO is a hard problem.
Yeah, I have a follow-up
Yes.
question of Joshua one. So we learned that your freshness is 3, 5, 7 minutes, right?
3 to 6 minutes.
What's the data completeness?
So same as in when traces are not complete and we can't see like the end event for something.
Yeah.
Or if we get the complete traces, then how
Well,
much
you
of
have a
those...
distributed system, right? You have heuristics to drop some long-running.
Yeah. Yep.
Yeah.
So the initial heuristic we used was 99.99% of, like some 99.9% of our traces would have X minutes of like silence time, which we like to call it, which is you don't see a span come in for X minutes, it means it's probably complete. So it's only like a 0 point something percent that is not within that heuristic. So the bigger issue is more that when people have really long traces, they're gonna get their data later. So we have a user configuration where if you know that you're that case, you can tell us some things so we can make sure we don't drop it.
Another question on bundling. Can you again explain what's the realistic example behind this bundling? Why do you need to trace sorry, when do you need to bundle kind of independent trace together? And follow-up question here, why do you reuse trace ID to tag seems to be yet another entity like DAG ID?
It is pretty much like a DAG ID, yeah, unless you have a trace bundle. So a realistic example of, let me go back here.
So is it just batching or is something else?
Mm-hmm. So queuing, oftentimes when you, let's say you've got 3 requests that started to execute some order, right? And then they got put on a queue. And then I've got a worker thread that is pulling them together as a batch, doing something with it, and forwarding it.
But
so
didn't they started like 3 requests from 3 different clients, 3 different independent clients?
Mm-hmm.
And I guess your client A from ABC wants to see their metric, not bundle it and mix it and merge it together with the ABC together.
Oh, that's not, so, okay, yeah. So these metrics are not separated at a, so I think so there's 2 different clients in our story, right? One client is the client of the system that our engineering teams are providing. The other client are the engineers that we are helping. So the engineers that we are helping, they're trying to see the data on like overall how their system is doing. Now, what they can do is they can do stuff like, actually, can you give me like my metrics grouped by or tagged by or aggregated by every client? In which case we can do that. We can have that be kind of, and we do that, which is like, we can extract that information from our spans if it's not sensitive. And then we can use that to further group those metrics together. So to answer your question, unless our user cares about that granularity of where this latency is coming from, we give them the overall view, or we let them tell us when to do it.
So my concern is that your end goal to show some percentiles on the latencies, and when you bundle together multiple traces and you take from the bundle the earliest start and latest end, and then aggregate that to find the percentile, that percentile is no longer a percentile of individual traces.
So that is not quite correct in the sense that when we're finding our latencies, let me see if I can quickly go back to this slide. So let's say this was a trace bundle, right?
Yeah.
So when we're finding our latencies across this, I will get one latency from this path. That's like, let's say 1 microseconds. Then I'll get another latency from this path. That's 2 microseconds. So what I'm bundling together, like I'm not actually bundling the latencies together.
Do you mean that each path is individual log entry that you shoot to the Dagger? Okay.
Yeah. So the latencies are not getting bundled. Just the spans are so that we can do this DFS stuff.
Cool.
Am I? Definitely over time. Okay, thank you everyone.